We are going to start with section 3.1. You'll see that 3.1 is titled 88 miles per hour. We are going to be dealing with slope as a rate of change. You can read through the first paragraph when you have a chance. We're going to start in the middle of the page under where it says class. They describe two different terms for us. They describe a rate and a ratio. A rate is a ratio that compares two different quantities. If you recall from before, ratios compare two of the same type of quantity. By rate of change, we mean a rate that compares the change in one quantity to the change in another. A speed like 88 miles per hour qualifies because we can write it as 88 miles over 1 hour. This quite literally compares a change in distance, that's the 88 miles, to a change in time, that's the 1 hour. That's exactly why we measure speed in miles per hour. The word equivalent in math means that two things are equivalent if they have the same value or are interchangeable even if they look different. So number 1 says if you made $100 a day for doing a certain job, how much money would you make in a 5-day work week? What do you need to do to solve this problem? We know that we're making $100 per day. How many days are we working for? We're working for 5, so we multiply by 5. What is 100 times 5? $500. Don't forget your label of the dollar sign. Number 2 then asks us if these two rates are equivalent. $100 per day and $500 in 5 days. Are those two rates equivalent? And what does that mean? Our answer is yes, they are equivalent. And they are equivalent because they both describe the same relationship between the number of days worked and the amount of money earned. The two fractions are equivalent. If we look, $500 in 5 days, it would reduce. We reduce all of our fractions. It would reduce to $100 in 1 day. Let's move on to page 284. It says question 2 demonstrates a useful fact about rates of change. They can be scaled up or down to fit a given situation. So the next set of problems asks us to write some rates of change slightly differently. Number 3 asks us to write a fraction equivalent to 60 miles over 4 hours so that I have a 2 in the bottom. So I'm trying to go from 60 over 4 to something over 2. What do I have to do to the 4 to turn it into a 2? Divide by 2. On a fraction, whatever I do to the bottom, I also do to the top. So the new numerator is 30. So the equivalent fraction here would be 30 miles in 2 hours. Go ahead and try the next one. The next one says we have the same fraction, 60 over 4, and now we want to write it so that I have a 1 in the bottom. What do I have to do to 4 to turn it into a 1? Divide it by what? Divide it by 4. Whatever you do to the bottom, you do to the top. So the new numerator is 15. My new rate is 15 miles in 1 hour. The next example asks us to go the other way. It asks me to take 320 over 4, and I'm trying to get to the point where I have a 10 in the denominator. Is there anything easy I can do to 4 to turn it into a 10? Some of you may see it. If you don't, let's do something slightly different. Let's turn this fraction into one that has a denominator of 1. So divide top and bottom by 4 to make a unit fraction. 320 divided by 4 is 80. So we have $80 per 1 day, which still isn't quite where they're asking me to get to. They want what on the bottom? They would like us to get to a 10 on the bottom. So now I have to multiply top and bottom by 10. So I would have $800 in 10 days. We have one more like that. This one asks us to take 40 miles in 3 hours and compare it to another rate of 50 miles in 4 hours. There are several ways you can compare these. You could turn them both into unit rates, which means we have a 1 on the bottom, and compare them that way. That's the scaling down. We could turn them both so they have the same denominator. The easiest way to get the same denominator would be to scale them up and scale them both up to 12, because I can multiply 3 by 4 to get 12 and 40 by 4 to get whatever I get for my new numerator. 40 times 4 is 160 over 12. So remember, that's miles per hour. My stylus is sticking a little bit. What would I have to multiply the 4 by to turn it into a 12? Top and bottom by 3. So my new rate for that one is 150 miles in 12 hours. So now we both have 12 hours. Which one is indeed going faster? The first one. So 40 miles in 3 hours is faster than 50 miles in 4 hours. Look below the orange box, and they give us some information. They tell us most experienced runners get to a point where they can comfortably jog at distances at a consistent pace. This pace, of course, is another way to say rate of change, because the speed is the rate at which distance changes compared to time. One particular runner jogs 1 lap around a 400-meter track in 2 minutes. We're going to assume that their pace stays the same. So for every 2 minutes, the runner jogs how far? 400 meters. So let's use this to complete the table. If they run 400 meters in 2 minutes, how far do they go in 4 minutes? Well, I'm going to double that, so it's going to be 800. Let's continue going up by 2s on the minutes. 6, 8, 10, and 12. So when they go 2 more minutes, they're going to go another 400 meters, which is 1,200 meters. You're going to continue to add 400 each time. These boxes are a little too small for my stylus to handle. Let's move over to page 285. It says, notice that the rate at which the runner's distance changes is constant. When the rate of change is constant, a quantity illustrates which type of growth. This goes back to that idea of exponential or linear growth that we dealt with in Unit 1. If it's staying constant, this is an example of linear growth. Let's write the runner's rate as a fraction using meters in the numerator. We know that this runner goes 400 meters in how long? 2 minutes. Let's turn this into a unit rate. Recall that a unit rate means we have a 1 in the denominator. So I have to take the fraction from above and divide top and bottom by what to give us a 1 on the bottom? Divide by 2. So my new numerator is 200 meters per 1 minute, or just per minute. So that gets us through number 11. Number 12 says to convert your rate to meters per second using dimensional analysis, so stuff that we had done back in the last unit. I want to take 200 meters per minute, and I'm trying to convert into meters per second. So I'm happy to keep my meters where they are. I want my minutes to go away, so I need minutes on top, seconds on the bottom. What do I know about the relationship between minutes and seconds? I know that 1 minute is 60 seconds. My minutes cancel, and I will be left with meters per second. Go ahead and use your calculator, and you do get 3.33. We're rounding to 2 decimal places. And don't forget your label, meters per second. Using this information, they ask us, what distance will the runner cover in 40 minutes? Well, we're back to the original one. We're back to 200 meters per minute. How many minutes is my runner running for? 40 minutes. You'll notice, just like in our dimensional analysis problem, my minutes will cross off. I'll be left with just meters. And the answer is that the runner will run 8,000 meters. What distance will the runner cover? This is number 14. In 40 seconds. I have to use the answer I found in number 12. So 3.33 meters per second times how many seconds? 40 seconds. You'll notice now that seconds cancel off, and I'm left with just meters. And my answer ends up being approximately 133.2 meters. Based on the previous two questions, can you write a formula for finding the distance traveled by an object when you know the speed and the amount of time traveling? The formula is going to be distance equals speed times time. Some of you may recall this from a previous math course as distance equals rate times time, and that works as well. Let's turn to the last question on number 16 on page 286. This one says, what would the runner's total time be for a 10K race? And they give you some information that you know. The first thing we're going to do is start with the fact that the runner is running 10 kilometers. Everything I know is in terms of meters, so the first thing I'd like to do is get rid of kilometers, so it goes on the bottom, and turn it into meters. What do I know? I do know that there's 1,000 meters in 1 kilometer. At this point, my kilometers left out, cross out, and I'm left with meters. Good progress, not the answer to the question. They do want to know what their time will be. So now I've got to go back to what my rate is. I know my rate is 200 meters per minute, but this time I need meters on the bottom and minutes on the top so that meters will cancel out. So 1 minute was 200 meters. Recall that we can flip those fractions, they're equivalent. Now meters cross off and I'm left with simply minutes. Now run the work on your calculator. Multiply 10 times 1,000 and then divide by 200. And we do get that the runner should take 50 minutes. At this time, you can go ahead and work on the group work, and that will be submitted to your instructor.